We are now. Thank you for reminding me. Okay, so the question is, when I put the model together, I did it like this. Oops. And on the n equals 2 and on the n equals 2 and the n equals 3 levels, I put these little lines here. Now the reason that I did that is because it's a little bit more correct to do this. Okay, so I'm going to show you what it's a little bit closer to in the Bohr model, and hopefully you'll see that the lines that I drew earlier were the lesser of two evils. So all of the black rings are the S levels. All of the blue rings are the P levels. And all of the orange rings are going to be all of the D levels. So this is n equals, this is n equals 1, this is n equals 2, and this is n equals 3. Okay? This is 1s, this is 2s, and 2p, and then 3s, 3p, and 3d. Does that make sense? I didn't want to put so many rings when I was first introducing this because it can be a little bit confusing. So what I did was I collapsed them into n equals 1, n equals 2, n equals 3, and instead of putting an entirely different ring there, I just said, hey, guess what? All the S stuff is in here, and the 3S level is all confined here, and then the 3P can be everywhere else. Part of the reason for that is I wanted you to kind of get, if you read it in your book, you'll see there's something called the octet rule, which is actually not correctly defined. But anyway, the general idea behind it is that for like the n equals 2, you're going to end up with basically 8 electrons that interact with the world around them, right? On the n equals 1 level, there's only 2 electrons that don't generally interact with the world around them, unless it's a hydrogen. But other atoms have more electrons than hydrogen and helium do, right? So they have a tendency to interact with the world with their outer electrons here. But we have to remember that that's not 8 electrons that are all sort of on equal footing. 2 of these electrons are in the S shell, and 6 of them are in the P shell, right? No, that's okay, Autumn. There are probably going to be a lot of questions, though. Make sure that you get them all answered to Thursday if you're not here today. Okay, so anyway, the way that I did that was just by dividing them. Does that make sense? If it's more visually appealing to you to create several rings, you can do that instead. So the Bohr model is not a real representation of the atom. It's just a model. The real representation of the atom is very odd and weird. And so we use this one to simplify it. So you can use a line if you want. You can use more than one ring for the n equals 2 shell if you want. I think it's more important to keep the terminology straight. Or, another way to think about this would be instead of having rings, you could say, okay, here is my nucleus, right? With as many protons or whatever, and neutrons and crap. And then what I can do is say, let's create a region for my n equals 1. Okay. N equals 1 exists all in here. So it's all like, this is the n equals 1 region. Okay. And then I can create another region for my n equals 2. So I might say, putting dotted lines so that you know that this is just, all I'm doing is just making a little, like a fence, like a yard for the electrons to play around in, right? So there's my n equals 2 region. So that's another way to kind of look at this. I can have electrons that are in the 1s shell, so this is n equals 1, right? This is n equals 2. And then you can define the s and p subshells of the n equals 2 shell however you like. So you can say then, like, if you wanted to imagine the electrons as plastered to the inside of this yard, like barking at the electrons over here as the 2s electrons, that's fine too, you know, and then plastered to the outside would be the p. You could do that if you wanted. It doesn't really matter how you decide to look at them. The important thing is to understand that the energies on these are on the p shell electrons, on the n equals 2 electrons, the ones in this yard out here, are around the same, all of them. They're a little bit different from one another, but basically they're all the same. So, I mean, there's just so many different ways to think about this, and I encourage you to find one that works for you. But, you know, as for whether there's a ring or not a ring, there isn't really any rings, not in reality. So you can just make as many rings as help you to imagine that essentially at the n equals 1 level, you're allowed to have some, oops, well, you only got one box. At the n equals 1 level, you're allowed to have, you know, your 2 electrons in this box. At the n equals 2, you're up in energy. So as we climb higher on the page, we're climbing in energy as well, right? And so you'll get this many boxes where this one is S and these are P, right? And then when we get to the n equals 3, then this is just a different representation than our ring representation. So many boxes. So many. Yep. Let's see. That many. So we have the S, and then the P, and then the D. And it just keeps doing that, right? There's just more boxes for 4. I don't want to draw all the boxes that are on 4. So, and then you can just fill them up with electrons, you know, just like, here's 1, 2, 3, 4, 5, 6, 7, right? Okay. It's just energy. So, okay. Thank you for that question. If has anybody watched this week's videos? I don't know, they're a little. Yeah, it's about what? Oh yeah, yeah. I don't remember what plant it was, but there was a um, yeah, it was potassium in the milk got exchanged for cesium. I think it was. It was a long time ago though. It was like we're talking 25 years ago or something like that. So no, it's more of a biological problem. This was like and the point of that in the video was to let you know that, and this is actually a really good thing for us to have up on our page right now. If we have an atom that, okay, so let's actually do this. Um, no, wait, let's do this. I know it's well. The good news, Casey, is that all the videos for the semester are out. So like this is it, right? We're at the end. So whenever you do find time for those, you'll be at the end of at that light at the end of the tunnel. So um, okay, so this let's build a box up here. I don't want to draw all the boxes, but I'm going to do it like this. So like that. Here's S and P and so forth, right? I guess I'll go ahead and finish the P shell. Oh, subshell. Okay, so here is an atom. Can anybody tell me what atom this is, by the way? If it's a neutral atom. Hydrogen has one electron, right? Not the one over here, the one that's represented by our boxes. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons in my atom. Well, I mean, you're allowed to look at the periodic table. So. Here, let's peel this off of here. Y'all really gotta... Nice. So, y'all really gotta check out the P table. It's great. But yeah, we basically build up our electrons until we get to the atomic number 11. It's 11 protons, therefore 11 electrons. So sodium then is the atom that I just described, right? If we wanted to look at potassium, which has 19 electrons, let's go back and look at what this would look like for potassium. Try not to press the X on these things. I have to be careful. Okay, so let's look at what it's going to be for potassium. This is 11, right? So let's do 12, 13, 14, 15, 16, 17, 18. And then we don't fill up actually the D shell quite yet. It actually moves up to this first, and then it goes to the D shell, which is weird, and that's why I haven't talked that much about it. But so this is what happens with potassium. So it's got 19 electrons, and it actually looks a whole lot like our other atom. So in other words, when you have sodium or potassium, they both interact with the world in a very similar way. As a matter of fact, have you guys heard of new salt? Mm-hmm. Yeah, it's the salt substitute, right? All right. Uh, I could either look it up here or you could check the ingredients. I don't know if they'd actually tell you what's in it. but let's look at new salt. Yeah. New salt. What is new salt? Ingredients. Potassium chloride. Well, do you guys remember what we looked at with in videos about table salt? What is table salt? Mm-hmm. Yes. So we have sodium chloride as table salt. Potassium chloride is salt substitute. The idea is that because both of them, look at this, what we just did. We just made potassium here, right? With all of our electrons filled up to the 4, n equals 4 level, right? And in other words, we've got a bunch of kind of filled s&p orbitals. And then at the very top, we have another one with a brand new electron just hanging out on the end, right? Okay, and then right here, we have the same thing. A bunch of S&Ps filled with a brand new electron that's just hanging out on the end. In other words, they both are atoms with one electron that's just sort of flinging around on the outside. That is their chemistry. That is the way that they interact with the world. So when they both encounter a chlorine atom, the chlorine atom steals this electron, right? The chlorine atom steals that electron for the sodium, and then if we fill all this up to here for potassium, the chlorine atom instead just steals this electron from the potassium atom. So they have the same chemistry, roughly, right? So that's why they still taste like salt to you. Does that make sense? Yes. Or just better for you salt, because instead of, I mean, you have to have sodium, right? But we tend to get too much of it. And so what they're basically doing is supplying potassium to you instead. Now it is possible to get too much potassium. It's also problematic for some people who are taking blood pressure medications. So I mean, there are all kinds of things that you have to pay attention to. You can't just say, "Oh, this is good for me, and therefore I'm going to eat it," right? Um, you have to you have to think. So, in other words, though, this is a little better for you than table salt is, um, but it has very similar chemistry. So, too much of anything is bad. So, is that chickens? Geese? I don't know my birds. I see. That's really irresponsible of you. You know, geese are terrifying. Okay, they are too. I am. I'm gonna run in the other room. Okay, so is everybody familiar with the ionic bond that occurs for both table salt and for new salt or potassium chloride? What we just talked about is an ionic bond, and is everybody familiar with how that occurs? Well, that's cool. So our ionic bonds are kind of the easiest ones to think about. It's the covalent ones that are weird and difficult to imagine, but the ionic bonds are that's because they're simpler, right? There's no sharing. It's just I stole your electron, right? So that's kind of an important distinction to make. Now, can you tell if we look at a periodic table, which I deleted here, and I should, if we look at a periodic, wait, man, maybe no, I did, I deleted it. Okay. If we look at our periodic table again, can you tell me then if I'm to take, why did I type that out? That's what I get for trying to think and do at the same time. If I take say a carbon atom here, and I want to form an ionic bond with carbon. Not particularly easy to do, but if I want to find an ionic bond with carbon, or let's say with oxygen, oxygen's a good one too. It's an even better one. If I want to form an ionic bond with oxygen, what do I need to form it with? Let's leave hydrogen out of all of our conversations for now, because hydrogen is kind of a special thing. It's like the space filler of the universe. It just, which is kind of a pun I didn't mean to make, but all it does is just kind of like make up for the gaps and everything else. So we're gonna think about heavier atoms beyond helium, like from lithium on. Okay, so yeah, so we've got neon over here, but oxygen will not want to react with neon because neon's happy. It has no reason to interact with anything else. That's right. Yeah, they don't need you. Right. They're haughty. They're like, I got my own money. I'm fine, right? So, whereas everybody else on the periodic table has to figure out how to get along so that they can get what they want. Now, what does oxygen want more than anything else in life? Unfortunately, it doesn't, actually. It does not want to be free. It no, but that's kind of that's an interesting. So these want to be free. They don't want to touch anything else. They don't care about anybody else. They're happy the way they are. They don't form molecules. They just fly around like little billiard balls happily. They're okay. Yeah, it does need electrons. And now here's the thing. That's your hint. These are happy, right? Everybody wants to be these. If you're sulfur, you want to be argon. If you're carbon, you want to be neon. If you're tin, you want to be xenon, right? So everybody wants to be these. And as a matter of fact, so like if you're down here, if you're rubidium, then you don't want to be xenon because you're a whole lot closer, like in the old Pac-Man sense. It's a whole lot closer to go out the left side of the table and come back around the right side, right? 36 and 37 are quite close to each other. No, neutrons are kind of like uh, they're just baggage, but they don't really do anything. They're just baggage. They do. I mean, they do in the sense that they keep it stable, as we saw in the lab, right? They do keep the atoms stable, but other than wise, they don't really do anything. So they don't. Well, they're actually internal. So let's keep in mind that the what's happening with protons and neutrons is at the nuclear level and is quite small. Let's put this in perspective real quick because I appreciate you asking that. I'm going to come back to this periodic table, but let's put this in perspective real quick, okay? If we had an atom, and let's take a marble. You guys have played marbles before, or at least you've seen people play marbles. You know what a marble is. Um, Take a marble, that is, if you make that the size of a nucleus, then the size of the atom is a football field. Yes. So what's happening at the marble level is quite small and does not affect the chemistry. It's the football field that's interacting with other football fields that we're concerned about. The proton and the neutron, despite the fact that they are quite, they a proton and a neutron, let's see, for like a helium atom. A helium atom is like 8,000 parts of the mass of it are in the marble, and one part of the mass is in the football field. So it's very dense in the middle. All the protons and neutrons do is their own business down there in the core. The electrons are the ones that are going around interacting with things. That's where the chemistry comes from. Does that make sense? Yeah, sure. So now these big, like gigantic rings of electrons that we're dealing with, that's the ones that we're having to think about. It is true that the protons and the electrons tend to try to be the same. That's true, but that's just about charge neutrality, right? So the two things that the electrons want, or that the atoms want to do is they want to have their shells filled. In other words, they want to be here, and they also want to be neutral. Well, they can't have it both ways, right? So the oxygen, it wants really badly to be neon. It never will be, but it can gain 2 electrons and pretend like it's neon. Of course, then it will be negatively charged, right? Because it's got extra electrons on it, right? So what is it going to do about it? Well, it would want to join up with something that has those 2 electrons so that it can steal it from it, and then that would be positively charged. So, for instance, magnesium. So if you have magnesium and oxygen, then let's draw this out. Let's look at the way this is going to look. We have, let's see, magnesium has a positive charge of 12, and oxygen has a positive charge of 8, and then they have these electrons, right? So the electrons are going to be taking away from this positive charge, right? If we, should we fill up our, I'm trying to think of the best way to represent this. Let's do it like this. The oxygen has, on the n equals 1 level, it has an electron here and an electron here, right? And then on the next level, it has a electron here, electron here, electron here, electron here, electron here, electron here, right? 6 of them. right? In total, it has 8 electrons. And it wants to have 2 more in order to be complete, right? If it filled those, it would be just like neon, at least in its mind, right? So magnesium, on the other hand, we fill these up pretty much the same way, right? There's this, and then there's this, and this, and this, and this, and this, this. Did I get that right? Yeah. Okay. And then it goes to the next layer. I don't want to do that because that looks weird. It goes to the next layer. But the next layer for magnesium, it has some extra electrons just sort of hanging out on the outside, right? Because this is magnesium right here. Okay, number 12. So it's got 12 electrons. It's got these two hanging out on the outside. Does that make sense? Oxygen looks at this and says, whoa, that's exactly what I need. I'm going to take this guy and put him right there, this one and put him right there, right? And so then you get a total charge for your oxygen of, once you get rid of these and you put them here, -1, -1. I shouldn't put that in red, should I? -1, -1. You now have a total charge here of +8 and -10, and a total charge here of +12 and -10. Because you only have 10 electrons now, because 2 of them were stolen. And then this one has 2 extra electrons, so it's -10, right? Okay, let's draw a line here. What's the what's the net charge of our oxygen now that it's stolen its 2 electrons? It's got +8 here and -10 here, so its net charge is what? Right, has a net charge of -2. And a net charge of this one. Yes, so they're attracted to each other because one's positive and one's negative. And they form a bond, right? So it forms a perfect ionic bond. And you would get 1 magnesium for every oxygen in your magnesium oxide. Okay? So here's what you're basically doing in your mind. You're saying, okay, this one needs 2 electrons, 1, 2, to get to the happy column. And then this one has 2 electrons, 1, 2, right? Now you could do that. It doesn't have to. They don't both have to go to neon. You could say potassium and oxygen could also form up. So calcium and oxygen could also form up. So you'd say oxygen needs 2 electrons, 1, 2, right? And then calcium would be like, oh, let me give you 1, 2. And then calcium would look like kind of like argon because it lost 2 electrons, while oxygen looked like neon because it gained 2 electrons. They won't be neon and argon, but their electrons will kind of look like it. Filled shells. Does that make sense? Okay, so what you can see then is that fluorine, chlorine, bromine, iodine, they have a tendency to want to form up ionically with lithium, sodium, potassium, rubidium, right? While oxygen, sulfur, selenium, tellurium have a tendency to want to form up with beryllium, magnesium, calcium, strontium. Does that make sense? Okay. It gets a little weird after that. Nitrogen and all of those, they form up with all kinds of stuff in different ways. So those are going to form ionic bonds for that reason, because essentially what we're seeing happen is that they straight up steal the electrons. There's no confusion about it. The oxygen's like, this is mine now, right? And even so much that if you've watched all the way through, you see if you throw this magnesium oxide into a solution, into water, they'll separate, and the oxygen's like, yeah, I'm going to keep these. So it just wanders around in the solution with these extra negative electrons, right? Of course, other things interact with it. The story doesn't end there, but certainly magnesium never sees its electrons again. It wanders off somewhere else, right? And tries to find happiness somewhere else. So that's just a straight up, very simple, I took your electrons. When it comes to covalent bonding, it's a little bit more of a complicated story, right? They have to share. Okay. So oxygen can form covalent bonds with other things as well. For instance, nitrogen can form, like you can form a covalent bond. It's a little bit more variable in the way that it can happen because there's many ways to share, right? I mean, I don't know if I'm bringing up anything sensitive for anybody, but you can kind of think of it like custodial arrangements, right? Um, an ionic bond would be like, I have the kids now, right? Where the electrons are the kids, right? Oxygen's like, I'm taking these two kids, and the magnesium's like, well, crap, okay. Like it never sees them ever, right? And then, like in the case of a covalent system, then it's like, well, if you form nitrogen and oxygen together, they're not going to be pleased with one of them taking the electrons. They want the electrons. They're going to have to find an arrangement where they share them. And so, for one arrangement, you get like one nitrogen and one oxygen, and that's what they call that? What's the old name? I'm trying to remember. It's not nitrous oxide. I believe they would call it nitric oxide. So it's just one nitrogen and one oxygen. It's also possible to have two nitrogens and an oxygen, which is nitrous oxide. So there are two different ways to share, right? When you have uh, when you have nitrogen and a nitrogen both sharing with the oxygen, it's a different way of sharing than the case of oxygen with one nitrogen, right? Does that make sense? They're going to have different because they behave differently, because they have different energies and different ways for the electrons to kind of uh, be shared between the two. They have different interactions with the world. One of these is poisonous to us, and it's what you have carbon monoxide detectors for, right? Or is nitrous that it's basically the same concept as as carbon monoxide, like it's poisonous to you. And then this one they use as like you can use laughing gas, right? You can just use it at the dentist. It's not so bad. It just makes you a little loopy. So like this chemistry is quite important between the two, right? Oh my gosh, I have a terrible experience in that area. It's okay, it was a long time ago. Oh, yeah. I'll see if I can remember what dentist it is so you don't ever go there. But it's anyway, so what I mean by arrangements here is that, like essentially, in this case, you're going to end up with oxygen gets the electrons a little bit more often than the nitrogen does, but only a little bit. They don't share it 50-50, right? So, and in this case, you're going to get the nitrogens actually get each their electrons a little bit more often than the oxygen does, but overall, the oxygen gets a lot of time with electrons because it gets to share with two of them. So I hope you can see the parallel that I'm drawing there with kids, like in the custodial arrangements and everything. It really is quite a bit like that. And so electrons always feel loved, though. What's that? Oh, I knew this was going to happen. All the electrons are loved. Does that make it okay? Okay. In any case, okay, so that's covalent, like co-parenting, covalent, right? Yes. Correct. Oh, I sometimes misspeak, so there's a chance that I might have misspoken, but carbon and carbon have to share. There's no way that one of them donated an electron to the other. Yeah. Now the reason for this is we can look at the valency of carbon. Now, do you remember how to do valency? So it shouldn't, hopefully, by the time we're done with this week, you won't even need to look at notes. All you have to do is you say, what row is carbon on? It's on row 2. Okay, so let's go to row 2 and count, right? We go 1, 2, 3, 4. It has a valency of 4. Does that make sense? Chlorine, on the other hand, would be 1, 2, 3, 4, 5, 6, 7. Does that make sense? Okay, so carbon has a valency of 4, which means it's got these 4 electrons just sort of hanging out on the outside, okay? Which means if it wants to have 8 electrons, here's your carbon. It's got an electron up here. Let's say it's got one. Here's actually kind of the way that we do it. There's an electron. Here's an electron coming at you. There's an electron going away from you on that side. There's an electron going away from you on that side. So it's got these 4 electrons just sort of hanging out on the outer side. And then if you get a carbon that's up here, then it's like, hey, I'll tell you what, I have one of these too, right? And then I also have these. So I have one there, and I have one going away, and then one going away, just like you do, right? And then another carbon's over here going, hey, dude, I also have one of these, and then some more out here. And another carbon's right here, very close to us. Let's draw a big C, because that one's very close to us, right? And it's like, hey, I've got an electron. I can lend you too, right? We'll share these equally, 50-50 time, right? And then another carbon is back here going, hey, I also have an electron. So what you can see here is that they form a network, and each of these is like a carbon out here that's like, hey, I can help. And they just keep doing this, and they form all these very strong bonds, equally strong bonds with each other. Now, if we are to look at this one carbon and let's say, hey, how you doing, carbon? It's going to be like, dude, I'm really happy right now because I have all my friends. I have 8 electrons. So I've filled. It's like my life is like a neon atom because I have 8 electrons. And they don't have to worry about being like a little bit negative or positive because they all share electrons, and so there's always exactly the number of electrons and exactly the amount of charge that all of them want. So it's a very stable substance. Yeah. It's kind of an iterative process because if I had drawn this for you from in the beginning, you'd have been like, what the hell are you doing? Like this. But after looking at it for a while, this hopefully makes a little bit more sense. Okay. It's all about sharing. Hmm? No. That, okay. Uh, let's see. So if we had water, now we are going to return back to the hydrogen conversation, okay? Hydrogen's a good filler. It does, As a matter of fact, those carbon that we just had diamond there, if you have carbon and you have two carbons that form, right? You have two carbons and you let them form a bond between them, okay? That bond means that they're sharing electrons, okay? This carbon is not quite happy because, like we saw before, what it really wants is a whole bunch of carbons to form bonds with, okay? But it doesn't have any more carbons available to it, so it's going to be like, hey, I have all these bonds that need filling. And this one's going to be like, me too, man. Me too, brother. I've got some bonds that need to be filled too. Hydrogen is always the thing that comes in and is like, okay, right? I'll, I'll be there for you, right? So, like, hydrogen tends to form up on this, and this is, in fact, uh, an ethane molecule. Um, so anyway, uh, hydrogen just kind of fills. It's a filler. That's what I mean by it's a filler. If hydrogen's available and you and you provide bonds, then that needs something to stick to. Hydrogen's like, I'd be more than happy to, right? So for oxygen, if you have an oxygen atom, then it's looking for some electrons, and hydrogen is like, well, it's got some, bonds there. It's like reaching out, hey, does anybody want to connect? I need some electrons. And hydrogen's like, sure. So it forms water, right? But since oxygen is so greedy, what it does is it's most of the time the negative charge of the electrons is spent over here on the oxygen. So it's a little bit more negative on this side and a little bit more positive on this side because the hydrogens don't get their electrons as often as the oxygen does. This is what makes water such a good solvent. It's called a polar molecule. So it's kind of interesting that this is an example of if you were to graph out, like, let's take a bar over here and graph out, like, I'm going to make it very dark where electrons spend a lot of time and very light where electrons don't spend a lot of time. So they'd be like this, right? And that's what makes it polar, and that's what makes it, it gives it a lot of features, actually. A lot of features to water are due to this. So, okay, this is actually what I referred to before when I said you can get a nice, if you have a faucet, uh, and you have water coming from the faucet, and you make a nice even stream of water coming from the faucet, and then you put something that's charged like a comb next to it, then it will cause the water to bend like this because of this action, because it's polar, is the reason that it does that. Anyway, this is just an example of electron sharing and how it's not fair in this example. But in our carbon example, it was fairly shared. They both got 50% of the time. I don't know whether this is helpful or not. I'm trying to kind of give you different outlooks, different perspectives on the same thing over and over so that you can kind of get a sense it's a very simple system. Well, I should say, here at n equals 4, things start to get very complicated. But above, about halfway up the periodic table, above that halfway line, things are pretty simple. And so, we really should just look at those simple rules, those 2 simple rules that I mentioned in the video. All of these atoms want to be have their s and p orbitals filled, and all of these atoms also would like to not be charged positively or negatively. What's our comment? Nice. Let's open this up. Mr. Gene gave us a there it is right there. The water's bending the wrong way, but yeah, that's the way that the why is it bending the other way? That's weird. It should bend to the left here because these negatives and these positives are very close to each other and it will be attracted. Does that make sense? Thanks, Mr. Gene. That's great. What was the dang it for? Oh, yeah, I don't know what happened there. That's weird. Anyway, all right, Cybob. Is Cybob got a better... Oops. Get rid of that. Hey, cool. Y'all can... yeah. If you don't have a head full of clean, dry hair, you can always use a cat. Find a cat. Not a dog, because I mean you don't want to be mean to dogs. Okay, so is this concept starting to become clear? Really, I don't want you to focus way too much on all the specifics because there are just too many. And we'll never run out of specifics. There will never run out of consequences of this behavior. But we can always begin at those 2 basic rules that, oxygen can be happy when it gets these 2 electrons, but it will still be a little bit unhappy because it's not entirely neutral. So it finds something that's equally positive to be happy with, and we formed an ion. And then some of these, all of these in this region here have a tendency to share electrons rather than steal electrons, right? From each other anyway, right? They'll steal electrons from these guys over here, but over here they just tend to share electrons because they're not pushovers like the like the ones over here, right? And then you can tell where's the I gave you an image in the video, but it's like this, something like this, right? Where you can see how tall the columns are here. That's how electronegative they are. That's how badly they want to gain electrons. And so if you have something tall, like this fluorine up here, it wants to form ionic bonds with these very short ones down here. It will form a little bit ionically with some of these mid-sized ones here, but as you can see, if things are around the same height, they're not going to form ions with each other. There's no point. They just form covalent bonds with each other over here in the yellow. Does that make sense? Okay. See, that's the kind of stuff that I want you to have a good sense of. Good. Good, good, good. Excellent. Okay, guys. I will still be here. between now and Thursday. If anybody wants, I can, because I know we're approaching the end of the semester. We're in a bit of a complicated topic. I know that. So if anybody wants to meet tomorrow at 11, I'll be available then too. And just let me know. Otherwise, I won't show up. So if anybody wants me to be here, I'm here for you. So just let me know. And hit me with questions. Make sure you look at that summary video. That's really helps to kind of put together everything that's. There are a couple of words that your book mentions that I don't mention in the first 3 videos that still bring up the concepts. Like, for instance, in the first 3 videos, I talk about protons in solutions, but I don't talk about hydronium ions. That's the same thing, and I explained that that's the same thing in the summary video. So the summary contains a touch of extra information, but for the most part, it just summarizes. Yes. Right. Both today's and Thursdays are going to be over those videos. And, well, I was just going to make sure that I reiterate to you that the first video for this week and the second video for this week contain mostly the information for today's quiz. And then the second quiz is sort of like all the videos. So. Yeah, the second video, the one on Thursday, is all the videos for this week. But today's quiz is mainly just if you make sure that you understand the information from the first and second videos, that should. It's kind of difficult to pull it apart. They're all kind of the same concept. Just I'm speaking about different aspects of it. So you would be safer to just watch all of them and then go back and make sure that you understand very well the concepts from the first video and the second video so that you can take today's quiz. Okay. I'm going to supply you guys with a one that you can sit down and do without having to do it online. And then I'm going to have you send me a PDF of it. You submit a PDF of it. I'll send you an email showing you how to do that. I've never had anybody say thank you for giving me an exam. That's how bad it's gotten this semester, isn't it? Oh, I put you guys a TikTok up. I don't know if you saw it. You don't have to have it to see the link. I've been making my demonstration videos for my classes on TikTok. I made you guys one last night, and you guys are talking good about cats, so I've got to I gotta give my counter argument. This demonstration had salt water, and I left it out, and this cat just got up here and started drinking the salt water, and then trying to knock over the salt, and then trying to knock over the glass bowl that it was previously in. It's a terrible animal. I don't know why you guys like cats so much. They're terrible. Rebecca's not believing. Dogs are amazing. Okay. All right, guys. Let me know if y'all got any more stuff that maybe questions, just anything that you run across. I want to make sure everybody's clear about everything, and I want everybody to make 100% on everything. All right. See you guys later. Well, take care.